Here we have neural network, artificial neural networks graphically, and we also have a artificial neural network based functions as shown right there. We have here input layer, output layer, and hidden layer in between, and we have to define sometime the feed forward networks. And how can we define feed forward networks? Of course, we can define feed forward networks graphically, as you see over here, where all the bias and weight metrics are shown right there, which connects the input layer to the first layer, and another one shown here to connect this first hidden layer, the next hidden layer, which is second hidden layers, and all the way you get to the last output layer. And of course this hidden layer, this weights and bias are connecting, and this hidden layer and the output layer, as you see over there. And this is the way we demonstrate a artificial neural network graphically. And there's another way that we express using a artificial neural network based functions, as you see over here. Okay, the network shown with red color represent a hidden layers, which is shown right there, and the W in here is these weight matrices that connects the input layers to the first hidden layers, and you have bias is at the end of each neurons, all the way one in the bottom. Okay, and again the one in blue color also represent a relationships between the first hidden layers and second hidden layer. So this is also a very convenient way to represent a artificial neural networks in function form. And all the feed forward networks here, feed forward networks all the way from here to here, should be expressed in terms of these weights and biases, and biases all the way towards the nth weights and nth bias and output, as you see over there. This is a output. So you can say why something like that here. So the feed forward network is absolutely important when you calculate the output layer, the output parameter in output layer, to calculate error functions from which you start a back propagation using a gradient descent to update your weights and biases, which is vital part of a artificial neural network. One of the example of this that you can see for defining feed forward networks, and this matrix is here, is this one you see. Okay, in the same color is this one you see, which connects the input layer to the first hidden layers, the neuron values. And these are very first matrix formulations. Represents the relationship between input layer and first layer. So these are the neural links, if you will, so that it connects neural values, one previous layer and one after layer. And one you see here is the matrix similar to one you see that represent between input layer and first layer. This weight matrix and biases also connects the neural values from first layer to the second layer. So this weights represents straight line here, and bias are adding all to the end of the neural values for second layer. And these are also called a neural links for second hidden layer. So this will continue all the way to the last layer, which is upper layer, so that let's assume that if we have a first layer, and red is represented by these expressions there, where W1 is this. Again, let me erase. W1 is this, and B1 is one that you add at the end of each neural values for the first layers, and the blue one, the blue function W2 represent this one, and bias is also added at the end of the neuron of second layer right here, and you continue these relationships all the way to n-1 layer and nth layer, and you have to multiply, of course, the activation function for every layers, and you're going to end up with the output there. So if you assume a n hidden layers, and you're going to need a n matrices to represent the feed-forward network calculation for n hidden layers. And if you have a one output layer, of course, then you need one matrix to also to represent the conclude a calculation of feed-forward networks. So that the feed-forward networks are represented by n hidden layers based on n matrices and one output layer based on one matrices. Of course, and the first layer is input layer. So the input layers shown in the very first matrix formulation here, right there. Let me raise a little bit here, right there. And this is the first wave matrix, and this is a input layer. So the input layers are shown in very first matrix. So we have a couple of ways to demonstrate and define a artificial neural networks. First of all, we can use a graphical networks, graphically like this, and this is kind of topology of artificial neural networks. Second way we do this is to use a equations, either in mathematical expressions or matrix formulations. They are identical matrix formulations, and you see over there. And third, probably use a ANN based functions, and we see here this one. Okay, let me erase again everything. This one. Okay, and this is a very convenient way for us to define the feed-forward neural networks. Okay, and these are the ways that we define the artificial neural networks, especially for the feed-forward networks. And the structural designs now can employ ANN based design method. I believe that this is very new and innovative way, innovative way. Also, it can be a stepping stone of next structural analysis and design that combines the mathematics, which is AI, with a structural engineering, so that we can perform very diverse calculations, find out input and output parameters, not using a structural mechanics but based on the big data sets and AI.